Assalamu alaikum wa rahmatullahi wa barakatuhu. Ya Banat, for you, there is no need for any introduction being my kids, but for those who might watch the video later, my name is Salih Lukman, an assistant professor of civil engineering at the University of Hafr al-Batin, and I am here to teach my kids introductory physics. Lesson 1. This is the outline of introduction, definition, and units. What is my motivation for teaching my kids physics? First, teaching physics as a hobby. Some 30 years ago, exactly in 1995, I was an SS1 student, just like you. Two of you are in SS1, and then Doge is an observer who is in JS2. This is my notebook, my SS1 physics, which I took with Malan Ibrahim Physics, a famous physics teacher at the time. And this is exactly what will be my guideline. So I was so fascinated by the way my teacher taught me physics at the time. He would come into the class, write the note offhand, move to one corner, and then start explaining. Since then, I developed interest in physics and had been teaching my my classmate at the time, physics, because of the interest that I developed. And here I am standing before you, teaching you the same physics. I started teaching physics officially in around 98, after I graduated from high school, that's secondary school, in 97. I joined from Muslim Refresher program. I joined the program as a teacher, started with primary 4, moved to primary 6, then JS1, and I think around 98, I started teaching SS1 physics. Some of the students I taught at the time are non-professors. One I learned is a professor of pharmacy that I taught physics in 98. And here I am standing before you to teach you, well, the same physics that I taught in 98 with some touch of modernity. Okay? So teaching physics is part of my hobby. I taught in also Muslim Potential Doctors Program, or MSTC, and as a professor of civil engineering also, teaching fluid mechanics, water engineering. I'm an applied physicist. Okay? So I love teaching physics. That is one. Two, one of my daughters, Mariam, had challenge with her physics, who is now in SS1 third term. Her first term physics result was a credit. Second term was pass. And then she came and told me that she does not understand physics. And for that, I thought I have to go back to physics class and make sure that she understands physics as much as possible. And that is what motivated me to start this physics class. Welcome to lesson 1. My teaching plan, I will start with introducing the concept, analyze it, introduce it with examples, both simple and to some extent, we may touch some advanced topics in order to corroborate the practical application or significance of a given concept. As the case may be, we may touch on some historical perspectives depending on what we are talking about, so as to understand, how some of these concepts were developed. Okay? And for one, I like history. I remember when I was in secondary school, I used to go to Kofandoka Library. They have encyclopedia of, the history of these scientists. So it's one of my hobby also, reading about, the scientific inquisition and discoveries of these scientists. Notable of them, you have Newton. Did you hear about Newton before? Hmm? Dude, Faraday. Did you hear about Faraday? Einstein. This is famous, right? Okay. The first one, Newton, you know, is considered like the father of physics. He practically like gave us physics into what it is today, in the basic form. Okay. He is the most, the best scientific genius the world has ever known. Lived about, 500 years now, 1642. Okay. And he was touted as, on his tomb, it was written that of all intellect, of all humans, there is no greater intellect. Okay. So he is the best theoretical and experimental physicist the world has ever known. Okay. Second, you have Faraday, who came in the 18th century after Newton. Okay. Who is the best experimental physicist the world has ever known. He didn't go to, public conventional school and knew no mathematics. The last is Einstein, who is the greatest scientist or the greatest genius of the 20th century. Okay? We may talk about him as well. Okay? And he is the greatest theoretical physicist the world has ever known. And Newton is two in one, Einstein and Faraday in one, isn't it? Because Einstein, the best what? Theoretical physicist. Faraday, the best what? Experimental physicist. And then Newton, the best experimental and theoretical physicist. Okay? So we will also have some numerical examples and discussions as we proceed. Okay? We have our board and you have your notebooks. So there will be some class works. We'll start with the basics definition. What is physics? Okay? Physics is the study of science, or is the science that studies matter, energy, and how they interact with each other. You see science written in yellow, right? Because it is a branch of science. You have to be a science student before you can study physics, okay? And then it studies two things, matter and energy, and how they interact. So the two keywords here are matter and energy, okay? Even though you might have come across what is matter and what is energy, but in this lesson, I will assume you have no basis of whatever I'm going to present. So I'm going to start from the very beginning, okay? So physics is the science that studies matter and energy and how they interact. So the first question someone would ask, okay, is what is matter? Okay, now we'll go into that, but then you have like this is a solid, liquid, gas, plasma. You know, when you add heat to solid, it melts, isn't it? It's like ice. When it comes out of the refrigerator, it gets heat from the surrounding and it melts into liquid. And when you put heat under the liquid, it can evaporate, isn't it, into water vapor to form gas. Okay? And then under certain conditions, when you now ionize the gas, okay, it can become plasma. We are going to talk about it. The plasma is simply what we see as fluorescent. They are charged gases. Charged, meaning they have been deionized into maybe positive and negative. Okay? Whereas a gas, in this case, it can be simply air or oxygen, O2. Okay? Physics helps us understand how things move, why they fall. I'm moving now. Why am I moving? If you throw something up, except if you are on the moon, if it's on the earth, it's going to fall down, isn't it? If you are on the moon, it may not fall down, isn't it? Because of the force of attraction. We're going to explain that later. And how light works. We all have light, fluorescent and all that, okay? We receive light from the sun as well. And how sound works, and even how the universe behaves. From the tiniest atoms to the biggest galaxies. I hope you know what is the universe. What is the universe? The world, isn't it? Consisting of galaxies, isn't it? And galaxies, we have over 2 trillion galaxies, correct? And in each galaxy, what is the name of our galaxy? Huh? The Milky Way, good. Which has over about 100 to 400 billion stars. Which star do you know? Madam, which star do you know? The sun. Excellent. So the sun is one of the stars in the Milky Way galaxy, isn't it? And we have over about 400 billion stars in the Milky Way galaxies. You understand? And there are over 2 trillion galaxies in the universe. Okay? So let's move on. So here it says physics is going to study from the tiniest, that is from the atom, even subatomic levels, that's the particles inside the atoms, and to the biggest, that's to the galaxies, okay, the stars. Okay? Now, in the definition, we said physics is the branch of science that studies matter and energy and their interaction. So we will take these two keywords. One is matter. Okay? What is matter? What is matter? What do you understand matter to be? Although I put it up there. Anything that has mass and takes up space. What is matter? What is matter? And occupy space. Okay, exactly what we have over there. But now let's break it down. Okay, with some examples. A rock is a matter, isn't it? Water, oh, is there. Water that we have here is a matter, isn't it? And then your body is a matter. All these three are visible. We can see them with our naked eyes, isn't it? But then, where it gets, not scary, but more interesting, we have ear. Can you see ear? Can you see ear with your naked eyes? Oh, so ear is also matter. Okay? But you can see, what air can do. Okay? We will explain that in greater details later. Oxygen, the air that we breathe, okay, is a matter. Carbon dioxide, the air we breathe out, is a matter. But all these three are what? Invisible. Invisible to the naked eyes, isn't it? We can't see them, correct? And they are all made of matter. Okay? That means matter is not something that you can see only. It comprises even those that your naked eyes cannot see them. You cannot see oxygen because it's air, isn't it? Correct? Water, you can see it. It's colorless, but you can see it because it's liquid, isn't it? Okay? That's very important. It goes to tell you that these our senses, our five senses, in science, they have some limitations, isn't it? Okay? Air was once thought to be an element. Air. Because previously, before the 18th century, when chemistry, there were advances in chemistry, there were just four elements: water, air, fire, and earth. And none of these are elements in the true sense of the word. Air, as we know, is a mixture of gases, isn't it? Okay? Oxygen, carbon dioxide, nitrogen, isn't it? And other inert gases. Mostly nitrogen, about 78%. Oxygen, about 20 to 21%, isn't it? Okay? So, there are things that is beyond the perception of our five senses, yet they exist. They are not spirits, okay? They are not spirits. There are things that we can actually like take them, study them under lab condition, okay? Oxygen, carbon dioxide, because we always take oxygen, okay? We breathe in oxygen and breathe out carbon dioxide, okay? Even though we breathe all the air, okay? Our system will selectively remove the oxygen in the air, okay? Now, matter is made of tiny particles called atoms, okay? And it exists in different states. I have started showing the different states of matter, okay? Solid, like ice, okay? Like this key. This key is a solid object, isn't it? And liquid, like water. Gas, like steam, water vapor. Plasma. I have started introducing plasma, which are charged gases. They are gases, but they are charged, ionized. Okay? When they are ionized, meaning that they have their charges. They are not combined like molecules. They are not inert. They are not chemically inert. They can react. Okay? And you have the examples, stars, lightning. When you see lightning, it is a plasma. Okay? The light the light we receive from the star is a plasma giant, and it emits radiant energy. Okay? The light we receive from the sun is also plasma. Okay? And fluorescence. The fluorescence, let me put one. Oh, this one, isn't it? Okay? This is an example of a plasma. There are gases inside. That's why when you try to break it, okay, the gas will escape and it will no longer work. Okay? They are placed under certain condition. They are deionized. Okay? This is plasma. Now, solid, like a block. Liquid, like the juice we take, gas, like balloon, you blow air into it, isn't it? And like I mentioned in physics, we don't rely on our five senses to establish the presence or absence of something. Okay? Why? Because nature is under no obligation to make sense to you, says Neil deGrasse Tyson. In physics, although at this level, more often than not, the things we are going to discuss are things that more often than not will make sense to you, perfect sense. But when you go deep into physics, there are things that, will appear as though they are magical, okay, myth, or completely unrealistic. And in the true sense of the word, they have been confirmed. They do exist, okay? So you have to put at the back of your mind that nature, the world as it is, and its operation is under no obligation to make sense to you. Okay? So if you hear something that, appears awkward or ridiculous, so long as it has been scientifically proven, then you don't say that, this doesn't make sense. Okay? Because your five senses have certain limitations. Okay? I cited a simple example of the air we breathe, isn't it? You can't see it, and it exists. And later we'll be talking about atmospheric pressure. That is the pressure exerted by the air on us, on everything on earth as well. Okay? Now, the question I want to ask is, which of them is the most abundant in the universe? There are four states of matter. Okay? During our time, we were taught three: solid, liquid, and gas. But later on, we realized that there is the fourth one called plasma. And only recently, as well, about a week or two, I read an article that says another state of matter has been discovered by Microsoft called topological state, using the quantum state, okay, using the quantum computers and all that, but we will not go into that, okay? So, but basically, you have four states of matter: solid, liquid, gas, and plasma. So, which of these do you think is the most abundant in the universe? And when I say the universe, I don't mean the earth. I define what the universe is, isn't it? The universe is the world, what we call the world, isn't it? Okay, which consists of over 2 trillion galaxies. Okay, with our own galaxy housing the sun consisting of about 400 billion stars, isn't it? So, which of them do you think, in your opinion, is the most abundant? Hello? Take the mic. Just tell me, which one do you think is the most abundant?
Plasma.
No, you're not asking me. You have to tell me, with confidence.
Gas.
Which one do you think is the most abundant? Is it plasma? Is your choice plasma? Talk now. Is your choice plasma?
Yes.
Okay, why? Okay, Mariam. What is your choice? Do you agree with her?
Yes.
Remember that you have to understand every slide, each and every slide, very well. You have to understand it in total. Okay? So, you agree that it's plasma? Dude.
What is abundant?
Abundant, that's presence of something in large supply. Plenty. Abundance means plentiful. Okay? So, plasma. Okay, why plasma? Why did you choose plasma?
Because of the
Because of what? You must have reason behind choosing plasma, right? Good. Say it out.
Because of the presence of billion of stars.
Presence of stars. Yes. Excellent. We said plasma is what plasma makes up stars, isn't it? Because stars are simply burning gases, like our sun consists of hydrogen and helium, or hydrogen undergoing a nuclear fusion, fusing into helium, isn't it? Okay, so, and stars are the gigantic structures that are present, the most gigantic structures in the universe, isn't it? So, if plasma is what makes stars, then definitely plasma is the most abundant on Earth, isn't it? Not on Earth, in the universe, isn't it? What about in the on Earth? What is most abundant on Earth between solid and on the surface of the Earth? Liquid. How many percent? Yeah, 75, 71, like that. Okay. So plasma is the most abundant because it makes up the stars. Okay? Is that clear? Although later on we may talk about something called dark energy, just as I mentioned, okay, dark energy and dark matter. Okay, there is something called dark energy and dark matter. When we will begin to talk about gravity, we will make a mention of them because these are advanced topics. Okay. Now, you see these three states: solid, liquid, gas. Okay, because plasma is also gas, isn't it? So that's why here we have just three classifications: Okay, solid, liquid, and gas. We will look at the molecules because matter, the smallest particle, the smallest part of a substance is called molecule. A molecule consists of two or more atoms, okay? Like oxygen, written as O2, isn't it? Meaning two atoms of oxygen makes one molecule of oxygen, all right? Like carbon dioxide, okay? CO2, okay? Two atoms of oxygen combining with one atom of carbon making carbon dioxide, isn't it? So that is a molecule. So these molecules are the smallest particles of substance that combine together to form either solid, liquid, or gas. We need to understand how these particles are arranged, okay? In solids, of course, they are closely packed together. They cannot move about, the molecules. They can only vibrate about their fixed position depending on the energy that they receive, okay? So they are fixed in position, but they can vibrate, okay, if they receive energy. In the next slide, I will talk about energy, okay? But the molecules and they have fixed shape and volume, okay? They have fixed shape, like, let's say this calculator, okay, you can see it's a rectangle, isn't it? So also all other, the shape can be regular or irregular, okay? You can have, like this board is rectangular, isn't it? So they have fixed shape and volume. You can find the volume of this board, isn't it? How? How can you find the volume of this board? How? Mariam. We said matter is anything that has mass and occupies space, isn't it? Occupying space here, we are talking about volume, okay? It has volume. So when you put it on your weighing balance, it has a mass, isn't it? Some kilogram like that, or grams as the case may be. And then you can find its volume, isn't it? How? Hello? How can you find the volume? Pardon? The volume of this solid whiteboard, rectangular,
LQ.
feel free to talk. Yes? How?
Volume for calculating a cuboid.
Cuboid, excellent. Which is the cross-sectional area times the width, isn't it? You find the cross-sectional area length times breadth, isn't it? Times the width or height or whatever, isn't it? That's the volume. If it's irregular object, you can find another way of finding the volume, isn't it? But the most important thing is that it has volume, isn't it? Now, in the case of liquid, the molecules in solid are closely linked together because the force of attraction between them is very high. Okay? What about in liquid? There are force of attraction between the molecules, but it is weaker. It is weaker than that of solid. Okay? So that is why the particles are not like attached to each other. Okay? Like that is a demonstration of the molecules in liquid. And molecules can flow under the action of shear stress, meaning when you pour it down, it flows. What about liquid? Solid. If I place this, come back 1,000 years, in the absence of any external forces, it remains there, isn't it? What about liquid? When I pour it, it moves, it deforms, okay? Because the molecules are not attached to each other. The force of attraction is weaker than compared to that in solid. Okay? The force is the force that binds them together. Imagine a magnet with a magnetic material. Okay? It binds to it, isn't it? Okay? So in gas, the force of attraction is very small compared to that in liquid. That's why you can see they are farther apart. Okay? And liquid also, it has volume. It has mass, of course, and then it has volume. But the volume it occupies, you can measure it. It fills whatever container, isn't it, that you fill. Okay? And gas as well, they are farther apart, the molecules, and they have volume. But you have to close it because when you open the container, they move out. because the force of attraction between the molecules in gas is very small. So they are free to move about. Okay, so in the macroscopic description, solids hold their shape, no need for a container, while for liquids, take the shape of the container and will stay in open container. In the case of gases, they expand to fill a closed container. No matter how small the amount of gas inside a container, they expand to fill the whole container. If you put them in small container, they will fill it. If you put them in large container, they will fill it. Okay? Simple example. This is what? Perfume, right?
Yes.
Is it liquid or solid or gas? What is inside?
Liquid.
Liquid, right? But what about if I... Do you think if I open it, it will remain liquid, or it will, it will be as if I open this water bottle? Will it remain if I open this one?
Yes.
Will it remain?
Yes.
It will not remain, it will evaporate because it is compressed gas. It appears as though it is liquid, but it is compressed gas, just like the cooking gas. That's why it's called liquefied natural gas. It is being liquefied. It is being compressed. When you compress gases, they become liquid. Just the same way, when you heat a solid, it changes to liquid and then to gas, isn't it? When you bring the gas, just imagine collecting water vapor or the steam. It collects on the top of the lid, isn't it? And it changes into liquid, isn't it? And falls back into the water that you are heating, isn't it? So this is gas, but compressed. So if you open it, in no time, it will just evaporate. Because it will fill the whole room. Do you understand? I'm just explaining that gases expand to fill a closed container. Okay, so that is why gases are always tightly closed in a container if you want to contain them. Even though the whole earth, we have gases around us called atmosphere. That is the air, okay? The air that we breathe, okay? Which consists of several gases I mentioned before. Nitrogen about 78%, oxygen about 21%, and then you have small percentage of carbon dioxide and other inert gases, isn't it? And this air exerts weight on us, on the earth, on everything that is on earth. Because air is matter, isn't it? We mentioned before. And matter has mass, right? So the air exerts weight on us. What do we call that weight on us? Atmospheric pressure. Okay? Atmospheric pressure. That is the weight exerted by the air on earth. Okay? We're going to explain what pressure is, because pressure now is the weight per unit area, isn't it? So the weight of air per unit area is what we call atmospheric pressure. And at sea level, that pressure is 101 kilopascal or Newton per square meter. Okay? We will explain that in details in the lessons to come. Are you following? I'm giving you, how the molecules are arranged in each of these three states. You have to understand them very well. Okay? Mobility of molecules, I explained that also. Molecules have low mobility because they are bound in a structure by strong intermolecular forces. And in liquids typically flow easily, even though there are strong intermolecular forces between them. For gases, molecules around freely move with little interaction during collisions. This is why gases expand to fill their container. Now, typical density. In the lessons to come, we will explain in details what is density. But briefly, density, we talk about mass, isn't it? We'll talk about also mass and weight, okay? Density is simply like mass per unit volume, okay? If you have a container, what mass can it fill, okay? And density is a measure of how, like, the weight, the heaviness of something. Let's say this water, okay? The density of water, clean water, clean water without contaminants, let's say this drinking water, could be around nearly 1,000 kilogram per meter cubed. Okay? Now, what about when I dissolve salt, table salt, or let's say sugar, or salt? Let me use salt. Okay? When I dissolve salt and stir, it will disappear, isn't it? It will dissolve. So if I dissolve salt, will the density remain the same? Why? Because the mass of the water will increase, isn't it? Because I have added another mass, which is the mass of the salt, isn't it? Although it has disappeared in the water, but the density of the water will increase because density is mass per unit volume. That is why the density of seawater is higher than the density of fresh water. Seawater density is about 1,024 and 24 kilogram per meter cubed because it has dissolved salts. Okay? And that also has other implications. Okay? That is why, like, you have what is called the Dead Sea. Okay? It is a lake. Okay? A lake, a saline, a brackish lake. Okay? Like, it's salty. So you can just lie and you float. Okay? Because of the density is higher than fresh water. If it's fresh water whose density is around 1,000, you may sink. You cannot float. We'll also discuss in greater details about density in lessons to come. But the density of solids are high because they have high mass, isn't it? For equal amount, usually. Okay, so like steel is about 7,700, water 1,000, air, density of air at sea level is 1.2. Now, so the density of water here is 1,000. The air inside the room, although we are not at sea level, okay, the density of the air is approximately 1.2 kilogram per meter cubed. It means, like, if you fill the air here, it means the mass, it has few molecules, isn't it? And water has higher molecule than air, isn't it? You can see from the demonstration. Whereas solid, for the same amount, usually solid have higher molecules. Although there could be some exceptions, even in the solid. You can have, there is one solid whose density is just close to that of air. But for most practical terms, most solids have higher densities than liquids, and liquids have higher densities than air. And even in the liquids, when you look at, let's say, organic liquids, let's say petroleum, kerosene, they are lighter, meaning they are less dense than water. All those organic chemicals, petroleum, kerosene, and all that, they are all lighter than water. Okay? And we'll explain that also when we go to density. Okay? Now, molecular spacing for solid, it is small. Molecules are close together. For liquid, it is also small, but they are held together by intermolecular forces. And for gases, they are large. On average, molecules are far apart. You need to understand this classification very well. That's why it is introductory physics. Okay? And then effect of shear stress, that is when you, let's say, try to press, to put, force, along it, okay? For solid, it creates deformation, it deforms, if it is deformable. Although anything can be deformed depending on the force that you apply, okay? We'll talk about shear stress also in subsequent topics, but this is just to the compare and contrast. For liquids, when you pour it, it flows. Simple. That is like shear stress, okay? It flows. That is deformation. And for gas, also it flows. When you open the container, they just escape. Simple. And effect of normal stress, they produce deformation associated with volume change. For gas, associated with volume change. All this other topics that we will take later. So that's why I will not take time to explain them in details now. Okay? And viscosity as well is one of the topics that we are going to discuss, which is simply like the friction in liquids. Okay, and of course, viscosity applies is the friction in liquids and gas. In solid, we call it solid friction. Okay, that's why it's not applicable to solids. Okay, because in solid we call it friction. Okay, and then in liquids, high decreases as temperature increases, and in gases increases as temperature increases. But I will not go into these details at this point. Okay, and compressibility, difficult to compress. Solid, isn't it? Solids are usually difficult to compress. Liquids also difficult to compress, but gases very easy to compress because of the spacing, okay, between them. Is that clear? Very clear. Hmm? Don't remember there will be questions at the end. Sorry, exercises. Okay. Now, we have been talking about matter all this while. Let's briefly now go to energy. You know, when you look at the universe, the physical universe, it means that everything is matter, isn't it? Correct? That means physics is going to study everything, each and everything, including your humble self. Okay? Although physics is not biology, okay, but in the human being, in the architecture of the human being, there are a lot of physics principles that exist. Okay? So physics is going to study from the tiniest, you know, that's the atoms, the molecules, to the biggest, the stars, the galaxies, and all that. Okay? Now, the other component of physics, which is equally important, is energy. Okay? And energy, let me ask you before introducing it, what do you think energy is? Just from your own understanding, what is energy? Yes? From your own understanding, what do you understand energy to be? If she doesn't have anything, yeah. What is energy?
Energy is the ability or the capacity to do work.
Good, excellent. Energy is the ability or the capacity to do work. Energy is the ability to do work or cause change. Because work, as we are going to define it clearly in physics, because we have work, energy, and power, for you to do work, you have to move a distance. Like now, if I hold a load on my head and stay at one place, I'm not doing any work. But if I hold it and then move through a distance, that is causing to move. Okay, causing some change. Okay, cause change. Then I'm doing work. Okay, so energy is the ability to do work. It's what makes things move, heat up, light up, or grow. Very important. Move, I have explained, you know, I move because I have energy. If I'm very hungry, you know, without sufficient energy, I may find it difficult to move, isn't it? Light up, we have the light, isn't it? We receive this light as a result of energy, isn't it? Which we are going to explain. Okay? And then heat up. Oh, I'm already sweating. I'm heating up, isn't it? Maybe because of the temperature. Okay? The temperature is probably hot, or because I am walking, I'm dissipating some energy as a result of talking, of moving, and other activities. Okay? And then grow. Energy is what makes things to grow, either as a human being or as plant. Okay? We are going to explain that. Now, examples: when you eat food, good, your body gets energy to run and play. Okay? And then a moving car uses energy from fuel. You have the petrol, isn't it? Or the PMS. And the sun gives off energy that warms the earth and helps plants to grow. Okay? Now, Energy comes in different forms. Though before we go to the forms, you see, you have petrol, which is a liquid, isn't it? Not water, but it's simply a liquid, isn't it? But it stores energy in the bonds, in the chemical bonds between the atoms. And that energy can be extracted when ignited inside the car engine. And the energy now moves the piston and the car can move. Is that clear? So that's, changing energy from chemical energy to mechanical energy, isn't it? In the form of the car, and that isn't it? So you have the chemical energy stored in the petrol, which is converted into mechanical energy because the car moves, isn't it? And then you have the sun. The sun radiates, gives us radiant energy, or what you may call light energy, or what you may also call electromagnetic energy. Okay, because the sun, like I said, is like a giant nuclear reactor. It has oxygen, it has, hydrogen, and then the hydrogen is fusing with another hydrogen molecule to form a hydrogen atom to form helium. And that process is called nuclear fusion. Okay, the process is called nuclear fusion. Okay, and the process is exothermic. It emits huge amount of energy, and that energy is what comes down to us, ultimately reaching the earth as sunlight. Okay, now you have also from a tree receiving the radiant energy and it converts it to chemical energy. Okay, because the plants also, they make their food. How? Through a process called photosynthesis. And photosynthesis, one of the requirements for photosynthesis to take place is sunlight. Yeah, the solar radiation in the sunlight, excites the chlorophyll to release electron, and then the process of food production for the plant takes place. It's a complex process. Okay, your biology teacher will tell you about it. Okay, but it's simply converting the radiant energy to chemical energy. So also when you have your mixer, okay, plugged, into an electrical source, getting energy from electricity, which is electrical energy, converting it to mechanical energy, as well as hammer. When you hammer a nail, you are converting, mechanical energy to heat energy. Okay, and then you also have your lamp plugged into an electrical source, isn't it? You have electrical energy being converted to light energy, okay, or radiant energy, okay, because the light we see here, or what we call the white light, okay, usually the white light, okay, as we know, it has 7 colors, isn't it? Although we have other colors before and after, isn't it? The UV and infrared, okay? We'll talk about that in details under light, okay, or optics. Now, energy comes in different forms, like the kinetic energy, energy of movement, okay? Kinetic energy is associated with velocity. Although in the next lesson, we'll talk about velocity, which is speed, simple, okay? Something must be moving before it possesses kinetic energy. It must have motion, okay? You have potential energy, which is the stored energy, like the energy in a stretched rubber, or the energy due to your position in a particular field. When you raise something up against, above the surface of the earth, it possesses potential energy. We are going to explain that as well. And thermal energy, which is giving us heat, okay? Light energy, or simply electromagnetic energy, or what is called the radiant energy, electrical energy, and other forms of energy. Now, is light a matter or energy? Yeah, is light a matter or energy? Light, is it matter or energy? Hello. You know light, right? Okay. The light we receive from the sun, sunlight, or the light we receive when we put on the bulb, fluorescent, or whatever it is. Okay? Is it matter or energy?
It's an energy.
It's an energy?
Yes.
Marioma?
It is an energy
Why not matter?
because it does not occupy space. If you cover it, it's not going to shine.
Okay. What about mass? Does light have mass?
No.
Okay. Later on under optics, we will realize light, the particles making light is called photon. Okay? And photon is massless. It does not have a mass. Okay? Now, but someone like when light is produced, I was talking about the nuclear reaction taking place inside the sun, at the core of the sun. That is where these photons are produced. When they are produced inside the core of the sun, they travel to the surface of the sun after millions of years, and then they travel from the surface of the sun to Earth. A journey of about 150 million kilometers in 500 seconds or 8.3 minutes. That is the journey that the photon undertake, okay, in 500 seconds. And then it hits our body, isn't it? The photon hit the surface of our body, isn't it? And then probably we feel warm, isn't it? When you're under the sun, correct? You feel warm because the energy of the photon is now, impacted, or is now converted, or is now absorbed by your surface. And it makes your molecules to vibrate. And heat is simply the average kinetic energy or the vibrational energy of the molecules. And the temperature rises. Okay? But the photon being massless, as we are going to see later, we are going to explain briefly something called relativity. It does not have time. I told you it travels 150 kilometers, right? In 500 seconds. But the photon does not have any sense of time. Time for the photon has stopped. Very funny, right? You can imagine someone saying time stops. How? Why? Because it travels at the speed of light. Okay? When you travel at the speed of light, let's say you enter into a space shuttle and projected at the speed of light. Time stop for you. Okay? Time will stop for you. Meaning you will go and come back to Earth when your sister Hello had aged. You see, now you are, let's say, the same age, isn't it? 14, right? Almost 14, 14. When you enter into a space shuttle and accelerated at the speed of light, come back after, let's say, some time, let's say 1 month, 1 month, at your own time, let's say 1 month, because time will stop for you. Halima would have been maybe 50 years older. And you will be the same age as you left Earth. The same age. Because time doesn't tick for you. But that is something, like I said, this is some of the advanced things that we will not go deep into, but you are supposed to hear about them, called relativity. Okay? Because time and space are relative. Okay? Your time, it depends on how far you are moving. Okay? If you move very fast, time stops. If you move very slow, then time slows down. Time slows down for you when you move very fast in space. Okay? So that is light as an energy, not a matter. Okay? Although it has properties of particle and wave. Okay? We will look at wave later. Now, sunlight versus solar radiation. We talk about solar radiation, isn't it? Okay, the energy released from the sun, isn't it? And sunlight, what we receive here on earth, isn't it? What is the difference between sunlight and solar radiation, or the radiant energy? Any difference? Hmm? Any difference? Hello? No difference. Yes, there is difference. Sunlight is the light we receive from the sun. I mean, that reaches the earth. Okay? It's the light that reaches the earth. Isn't? That's why we call it sunlight. We also have moonlight, isn't it? Okay? The light that we see at night due to the moon, correct? Which reaches the earth. But then solar radiation, I discussed about producing radiant energy by the sun, isn't it? I talk about the spectrum of light, isn't it? The visible spectrum, the different colors, isn't it? But you have, the ionizing radiation, the gamma rays, the X-rays. You know about X-rays, isn't it? The sun produces all the spectrum. That's why it is called electromagnetic energy. Okay, it produces the gamma rays, the X-rays, and the which one again? Yeah, X-rays, gamma rays, and then you have these are ionizing radiation. Okay. Oh, UV rays, ultraviolet rays. Okay, okay. These are ionizing. They rip off your atom. They break it down, isn't it? They cause cancer. Correct. But then, fortunately for us, they are filtered before they reach the earth. Okay? The X rays are filtered, the gamma rays are filtered, the UV rays, they are filtered by the ozone layer. Have you heard about ozone layer? Correct? It's a layer about maybe 15 kilometers. Yeah, about 15 kilometers above sea level. Okay? So the UV rays are filtered by the ozone layer. That only 1% is allowed. It breaks it down. I mean, because ozone is O3. So the energy of the UV rays is used in breaking down the ozone into oxygen and oxygen molecule, thereby, utilizing the energy of the UV rays. Only 1% reaches the earth. And that 1% is what we utilize. Okay, we absorb. Okay, our body absorbs, and then it produces vitamin D. Okay, the medical doctors will tell you more. They will say it's absorbed by the cholesterol, and then it undergoes other processes to produce vitamin D. So when we go under the sun and say we are absorbing vitamin D, we are not directly absorbing vitamin D, but we are absorbing the UV rays. Okay, they are the ones that kickstart, the process of the production of vitamin D in our body, which is the only vitamin that our body makes. The only vitamin that our body makes. But then absorbing too much UV rays means you can have skin cancer as well. Okay, that's why our black skin has melanin. It absorbs the UV rays. Okay, it absorbs the UV rays. And then that means we need to be under the sun more for us to produce enough vitamin D, because the melanin under our skin absorbs the UV rays. It deactivates it. So few amounts now is left for the production of vitamin D. Okay? Now that is, what about the other part of the electromagnetic spectrum, infrared, radio waves? They come down to earth. Infrared is what heats the earth, is the heating part of the light. You remember the light bulbs we used to have before? No, maybe you don't know them. The 100 watts, 70 watts, which were heating. When you touch them, they are very hot. They produce most of the light in the 90% in the infrared region. That's why they are heating. But then with technology, it is refined. We have the LED, isn't it? Which does not heat up, consumes less energy, because it produces most of the energy in the visible light region with very small amount of the infrared, because the infrared is the part of the light that is responsible for heating up. When you go under the sun, you feel hot, not because of UV rays. Not because of UV rays, it's because of the infrared part of the light. It's the one that is heating you up. Okay? And the earth also heats up because of that infrared. And the global warming is because of that infrared. Because it goes up, it blocks what are called greenhouse gases. Okay? The greenhouse gases cannot escape, which are the water vapor, the carbon dioxide. Okay, so it heats up. Okay, it heats up. It heats up the earth, and then you have the earth being warmed up. Okay, the earth is gradually becoming warmed up. Okay, and these gases, they go up and block the escape of the infrared rays. They block them. They trap them. So it's becoming warmed up. Okay, but this we will discuss in greater details under optics. Okay, but just know that sunlight is the filtered solar radiation, isn't it? Because what we receive here on Earth does not include X-rays, gamma rays, 1% of UV rays. And these are ionizing radiations, dangerous. Okay? So it's the filtered solar radiation reaching the earth that we call sunlight. You now understand the difference between solar radiation and sunlight. Clear, right? Now, talking about potential energy and kinetic energy, we'll soon round up. I think this is which slide? Oh, this is the 9th slide. You see, this is a cliff. You have a rock. The rock possesses potential energy at the top of the cliff, due to its position, okay, above the surface of the earth. Because potential energy, as we are going to learn, is mgh, okay, is depending on the height, okay. When you release it, at this point, the potential energy is 10 kilojoules, okay. Kinetic energy is 0 because it is not moving. I told you earlier that kinetic energy, for a body to possess kinetic energy, it has to be moving, isn't it? So the kinetic energy is 0 because V equals 0. But when you release this rock, as it is coming down, it's falling under gravity, isn't it? It is accelerating at a constant rate of 9.81 meter per second squared, isn't it? If something is accelerating, that means the velocity is increasing, isn't it? So as it is falling down, the velocity is increasing. So the kinetic energy is increasing, isn't it? From 0, it's increasing. The potential energy is decreasing because the height above the Earth's surface is decreasing, isn't it? But the total energy is still the same, 10. You see, at this point, the potential energy can be 7 kilojoule. It has reduced from 10. The kinetic energy has increased from 0 to 3. What about when it hits the ground? What is the potential energy? Hello. When the rock hits the ground, what is the value of the potential energy? 0. Excellent. Because the height is 0, isn't it? What about when it is just about to hit the ground? What is the value of the kinetic energy? Mariam? 10. Excellent. Because at that point, all the energy is kinetic. The potential is almost 0 at that point. And the total energy remains what? The same, right? Correct? And that takes us to the energy conservation. It started with 10 kilojoule. It ended up with 10 kilojoule. Although, when it hits the ground, the potential energy is 0. The kinetic is 0. What about the 10 kilojoule? Where does it go? Does that mean we lose energy? It goes into sound energy, heat energy. It will hit the surface and all that, isn't it? So it becomes like wasted energy. Okay? It is not lost because energy conservation, you can neither create it nor destroy it. So the energy is conserved. Although this is also a special topic that we will take under work energy and power. Okay? But energy is always conserved. And that takes us to the very beginning. We said matter, energy,